As we kind of go through this stuff, everybody always asks, oh, when are we ever going to use any of this stuff? Generally speaking, the right triangle trigonometry is one of the more useful and applicable situations in mathematics. You take a look at construction, engineering, anything that's your physical things like that applies to a lot of this. So it is there. Now we've talked about the good old SOHCAHTOA stuff, opposite over hypotenuse, B over C. And having that picture in your mind makes life a lot easier for setting this stuff up. So again, one of those little things that you should have there. Identify your theta, your hypotenuse, your opposite, and adjacent. And it doesn't matter what triangle that you have, always set that up. And when we throw it onto a coordinate grid, we always identify it being in the first quadrant. So a lot of this stuff is just simply write it down, set it up, solve. Okay? And like I said, we've played around with quite a bit of this already. So let's take a look at examples here and see if we can't make ourselves a rainbow. Let's go. So it's not what I wanted. That's all. Okay. So we're taking a look at a rain gutter to be constructed of aluminum sheets 12 inches wide. So again, a picture painting 1,000 words, definitely, definitely, definitely. So we've got that. We've got the 12 inches wide. Now it says after marking off a length of 4 inches from each end. So now we know that this is 4. We know that that is 4. And since the whole thing was supposed to be 12, what does that leave us on the inside then? 4. Okay. We know that this was all supposed to be 12. So now these are going to get bent up somehow or another. So we're just going to set that up here again. So we know that's 4. That's going to be 4. Now express the area of the opening as a function of theta. Now this bend here is what we are looking at. That's our theta. Because as this goes up, it changes, does it not? So what does the area look like of this? I draw this out across here. We know that this here is going to be what? Isn't that going to be the same as this height that's over here? So this is our opposite sign, correct? Opposite, right? This is adjacent, and that's hypotenuse. So if I want to find out what the opposite is, and I got a theta, well, what information do we have? We have hypotenuse and opposite, so that's going to be sine. So that means the sine of theta is going to be equal to what? What's the sine of theta going to be equal to? Isn't that opposite over 4? So, ha, Oh, okay, but you got to remember that we don't know what this distance is in here. This was 4 when it was straight, and as we fold it up, all I know is that this piece here is still going to be 4 inches. If you think about, take a sheet of paper and, fold it and then start bringing it up. This distance in here changes, okay? This distance here changes. So our adjacent and our opposite sides are going to be changing as we're going through and doing this. So if I want to calculate out the height of this, I need to know, or the area of this, I need to know what this is, which is the same as the opposite side, correct? So theta, I put something in and I am going to get opposite over hypotenuse, okay? That also means that if I want to go and figure out what the opposite is, it's simply going to be 4 sine of theta. Does that make sense to you? Is equal to the opposite. So if I want the area of this, the area of this box is going to be 4 multiplied by 4 sine of theta. That'll give me the area of that box. Would you agree with that? Base times height, right? Now, I also need to take care of the triangular piece that's up over here, okay? And that is base times height divided by 2, correct? But I have another one that's also going to be over here because this is going to be symmetrical, correct? So that means this A here is this A up over here. I already know how to get this. I need to know how to figure out the A. Well, that would be cosine, correct? So that would be the cosine of theta is going to be equal to the adjacent over what? Wouldn't that be over 4 again? Adjacent over hypotenuse. Now, I can't deal with this in terms of tangent because that's 2 unknowns in one thing. So this one turns out to be 4 cosine of theta. So for the triangles, I would have the base, which would be 4 cosine of theta multiplied by the height, which is sine, or 4 sine theta. Sorry, it's getting kind of messy there. Divided by 2, correct? But because I need 2 of them, multiplied by 2. So the 2's would cancel out. So I'm going to write this out here as 4 cosine theta. That's the base of the triangle. Multiplied by the height of the triangle, which is 4 sine of theta. Divided by 2, but I need 2 of these. So it's multiplied by 2. Plus the rectangle, which is 4 sine theta multiplied by 4. So if you want, you can go and simplify that out just a little bit. And honestly, what I could do, this would cancel off with this here. I see I got a 4 sine theta here, 4 sine theta here. So if I wanted to, I could factor out a 4 sine of theta and leave in here 4 cosine theta plus 4. That would simplify it out to put it into the graphing calculator, correct? So if I go back and I take a look at where they ended up at, they ended up putting it in like that because they didn't get rid of it. They went and took 4 times 4 and they worked it out and they multiplied it out like that. So let's see if I can actually come up with the same stuff that they've got. So grab the graphing calculator. Okay. Now we're working in terms of degrees, so we got to make sure that we switch our mode over into degrees. Otherwise, we're going to be having some rather interesting answers. So here, put that back up again. And I put in parentheses, 4 sine theta, close it, multiplied by 4 cosine theta, close it, plus 4, close it, window. Okay. So, 0, smallest angle. X is representing theta in this case. Would we want to go up to 180 degrees? No. Let's see, anything over 90 would cause it to tilt in, so that wouldn't work. So I'm just going to put this thing up to maximum of 90 degrees. Okay. Volume. Well, 0 volume. And if this thing was folded all the way up, that'd be 4 times 4, correct? 4 wide, 4 high, so that'd be 16. And so let's go up to say 32 just to be on the safe side, so we got enough room to work with. Graph. Quit. Window range. Oh, duh. That would be 0. That would be 32. Always helps if you put them in the correct order, right? Graph. So there we go. So now what we're looking for is the maximum value. So we want to go to max 4. Oh, that's a good place for the left bound. Right bound should be somewhere over here. And we go through and we do this, and it hits that x is equal to 60. So verify it out that 60 degrees is the maximum value. So what they're telling us is if this measurement here is 60 degrees, so it end up being 30 degrees, okay, that will give you the maximum volume. Okay. Make sense? You'll notice that these problems require an awful lot of thinking about what's going on with them, drawing it out, working it out. It simply takes time for this stuff. Now, complementary angles are equal. We've kind of seen that before when we were dealing with the unit circle, where we seen sine of 30 degrees, cosine of 60 degrees. These were the same values. Okay. They're going to go through and deal with, other little things. Sine of 62 degrees, well, that would be the sine, same as the sine of 28 degrees. Why? 62, 28 add up to 90. That's always what's going to be there. Radians, okay? Radian measure is pi over 2, correct? At 90 degrees. So again, keep those things in mind. So, Pythagorean theorem. Nothing new there. A plus B is equal to 90 degrees because we are working with the right triangle. So nothing new there. Nothing new over there. Width of a river. Okay. Let's talk about that one. Again, we're taking a look at the applications of this stuff. Where can I use it? How can it be used? Now, a surveyor can measure the width of a river by setting up a transit at point A on one side of the river, okay, sighting at point A, then turning through at an angle 90 degrees at C. So he's got his point, he's got it set at 90 degrees. He knows that it's on this line here, so he goes and measures out that this is going to be 200 meters. This here theta is going to be at 20. What is he looking for? He's looking for this particular distance right here. Okay. So which one of the trig ratios would work best here? Well, I don't know hypotenuse. Could figure it out if I really wanted to, but I'm only concerned about opposite and adjacent. So tangent of 20 degrees is going to be equal to the opposite, which is the distance across the river, divided by the adjacent, which is 200. So really all it's going to be is the tangent of 28 degrees multiplied by 200. So clear that out. Tangent 28 degrees multiplied by 200. Why did I put 28 in there? Oh, because I can't read my own writing. How's that? 20 degrees. Well, we were talking 28 degrees over there before. Hate it when things like that happen. Let's try that again. Tangent 20 degrees multiplied by 200. So it's approximately 72 meters across at that point in the river. That's how it's done. So inclination of a mountain trail. Same kind of an idea. Again, we want to try and draw these situations out. Now, granted, sometimes they give you a picture. Sometimes it's more helpful to not take the picture and go along with it and see what you got out of it. So, let's see. A straight trail leads from an alpine hotel, elevation 8,000 feet, to a scenic overlook, elevation 13 or 11,100 feet. Length of the trail is that. What is the inclination? Grade. Okay, so there's flat, right? So we're going up the hill. Now this distance, 14100. Because when we measure height, that's always going to be at a right angle to a center to a flat area. Now, mind you, this was here, this elevation was at 8,000. This elevation is at 11,100. So that means that it's 3,100 feet difference, correct? So now, we're looking for that angle, that theta. What would I use? Well, theta is here, this is adjacent, this is opposite, and that is the hypotenuse. So, sine. So sine theta is going to be equal to 3100 multiplied by 14,100. Right? Opposite over hypotenuse. That's all it's going to take. So that means for the calculator, we would end up having to use that inverse sine deal that we were talking about earlier. So we would go second inverse sine of 3100 divided by 14100. Close it. So we're looking at 12.7 degrees. Now it's talking about the inclination, the grade of the trail. So as we go through this, let's see. The grade is exactly the same thing as the degree measure. So this has got a grade of 12.7 degrees. There's all kinds of wonderful little things here, you know, height of the clouds, and statue on a building, different ways of using the information to figure out different types of problems. Bearing of an object, you know, what's the degree measure off, okay? But I want you to play with these, and we'll go through them as time goes on.